method. If you look at the engineering mathematics 1 syllabus, you may have done this numerically as well as analytically. But here we are not going to let you know the all the method Gauss-Seidel. No, we just use Gauss-Seidel step by step. You will see next slide and the following slides how Gauss-Seidel method can be used numerically to solve this problem. Take note, yeah, you cannot solve this analytically. So what is the meaning of numerically? Numerically meaning you must use the word is uh, iteration. Yeah, iteration. So what is this iteration? It will be explained. So you have to pay attention how we are going to solve this equation. Now you have to start with initial guess. This is only for Gauss-Seidel. So Gauss-Seidel, you must start with the initial guess. So how do we know the initial guess? You have to create on your own. And it is already mentioned the fact the T1, T2, T3, T4 superscript 1 is initial guess must be all 0. So if you don't have this initial guess, then you cannot start the iteration 1. Because for iteration 2, you no need to use the initial guess because we will use the iteration 1 output. So the important thing here is you have to use this initial guess. We have to be very particular about the subscript, yeah? T1, T2, T3, T4. This is the temperature. T0 and T5 is already given. So you don't worry about T0 and T5 because 0 to 10 meters. So the each interval is 2 meters, 4 meters, 6 meters, 8 meters. So the temperature at 2 meters, 4 meters, 6 meters, 8 meters, the starting temperature is 0. But the temperature at T subscript naught is 100 degrees Celsius. T subscript 5 is 0, 50. 50. 50 is given in the problem. You go back and see in the problem. This is T0 100, T10 50 degrees. But this temperature T0 rod is 0 is different. Is different. This is for the implicit method. But for the Gauss-Seidel, if you look at Gauss-Seidel, go back to the slide Gauss-Seidel under the topic Gauss-Seidel. This one. What I mean by the 0 is this one, the initial guess. We start the solution process choosing the initial guess. This is to solve the system of linear equation. So don't mix these two things here, implicit method and Gauss-Seidel method. Implicit method is to create, to construct the system of linear equation. That is the job of implicit method. But to solve the system, we use Gauss-Seidel method. So you may wonder how to solve using Gauss-Seidel. But this Gauss-Seidel, we want to use the numerical approach. So how do we do that? Using initial guess, you have this equation. This is the first row, T1, T2. From where? From the equation, first equation. So you are solving T11, T21. But the first value is T11. This one you want to find. Iteration 1. You cannot find T2. No. T11 first. Because this is the order. T11. This is the initial one. But iteration 1, you are starting now. Next. What is next value for T11? So the T11 is here. So T11 equals to left hand side equals to right hand side 2.08 0875 from the previous equation plus 0.020875 T21 divided by 1.04175. You must remember, yeah, this is a 100% numerical computation. It's called numerical experiment. So you must be well versed with the calculation by using calculator at the moment. Maybe in the future you can use the computer. So we have to spend more time on calculation, not the method. Method is already like this. This is Gauss-Seidel, how the flow will move next stage and so on. So the calculation is like this. So you use your calculator now, confirm with us, or validate or verify 2.0875 plus 0.020875 multiply 0 divided by 1.04175. You see here, T subscript 2 is 0. You take this value, put it here. This is called Gauss-Seidel iterative method. So you calculate this, you should be able to get 2.00384. Can you get that, class? Can anyone confirm this? 2.00384. Mohammed Amdan, are you there?
Yes, sir, I'm here.
Yeah. Somebody said slide 24. I think we already continue, right? No? Somebody said slide 24. Is there slide 24? Which
Yes, sir,
one is
right now
correct?
24.
No, which one is correct? Where we should start? Are you aware of 24 or 31?
24.
Huh? Who is that?
Gabriel. So we stop at slide 24 that day.
Who is that? Gabriel. Okay, okay. So, okay. So that means slide 24. Okay, okay. We go back. Sorry about that. Okay. So before that, because you must know the slide number 22, Gauss-Seidel method. Before that, you already this system. This is called implicit equation. Will be used to solve example 1 again. So example 1, we are going to use implicit method. That is the question. Sorry, Sorry, Yeah, internet problem class. Yeah, Chia, can you hear? Chia, can you hear? Can you see the slide now?
No, sir. For the slide, no.
Okay, okay. I have to internet problem, class. Internet problem, So we're having a problem here, internet problem. So the line is not good at my place. So bear in mind, yeah. So internet problem, yeah. So now can you see slide? Can you see the slide now?
Yes, sir. Now can.
Now, okay,
Yes.
Kelvin. Class, we're having a serious problem here, internet problem. So if a line cut off, we have to wait for some time. All right. So you told me to start off with the slide 24. Okay. Slide 24 is same example, previous example. The only difference is the method is different. So if you want to use implicit method, must remember implicit method involve construction of the system of linear equation, which is what we call algebraic metric equation, and then solve using Gauss-Seidel. This is new. So Gauss-Seidel is first time you're going to use to solve this heat conduction equation. The problem remain the same. Solve for the temperature distribution. That means the capital T for the long thin rod with the length 10 cm. And then given the step size, the distance del x is 2 cm and del t is 0.1 cm, 0.1 second. At the time small t0, the capital T temperature of the rod is 0. But the boundary condition is different. Now this one is already fixed. You cannot change this. What is the meaning of this? The temperature at x0, that means the distance when 0, then you have temperature 100. At distance 10, temperature 50. That's why some of you asking why you don't want to find the temperature at T0 and T5. We only find T1, T2, T3, T4. The reason is this one is given, so no need to find. So we want to find the temperature at T0.1. So 0.1 at T0.1 for x 2 cm, x 4 cm, x 6 cm, x 8 cm. Then you stop. So you have the matrix 4 by 4. So del lambda, you have to use this formula and you calculate. Now you can confirm with us. K multiply del t divided by del x squared. This formula you must memorize and it will be given. You must be very familiarize yourself with this formula. Otherwise cannot find the lambda. And if the values are not given, you can ask. You cannot create your own K value especially. Delta T maybe depends. If it's given, you use this 0.1. If it's not given, you have to find on your own. Delta X is 2. So this one all given. If it's not given, you cannot find. So that is the problem here. All must be given. So lambda, you can verify now, T 0.020875. And this one is not the initial guess. This is to develop the matrix, the linear equation. So this one comes from initial condition and boundary condition. The strange thing is this one, you see subscript 0. Of course, superscript 0 because we haven't started the level. So the level here is all superscript, all 0. But the most important thing is the subscript. This subscript T0 meaning temperature at the initial distance x. X is 0. And then that is 100 degrees Celsius. In between, all 0. But the T5 is when x equivalent to 10 cm. You see, x runs from 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. So when x is 10, the temperature is T subscript 5, is 50 degrees, is already given. So there will be some confusion when you substitute this value. You have to be very careful because this is not 0. This is 150. So now we use this equation. This equation, T superscript L plus 1 or left hand side. You get this equation from where? From the previous system which we created here. You see, L plus 1 or left hand side. T superscript L right hand side. This equation will be given. You no need to memorize. So what you do, you just take that equation, put it here, and then substitute all the values. Minus lambda. L here is 0. So you write down here, L is 0. So you start with I1. I1 meaning at x 2 cm. So I cannot be 0 because inside the formula, I must be start with 1. So 1 minus 1, 0. So T1, 0 minus lambda plus 1 plus 2 lambda. T superscript L. L plus 1, 1. Subscript I1 minus lambda. T superscript L, 0 plus 1, 1. Subscript 1 plus 1, 2. T superscript 0, subscript 1. So this value, you want to find T1, T2. Superscript 1, 1 is the next one. T1, 0, this is given already. This value is 0. And lambda, T1, 0, this one actually is T0, is 100. It's same as this one. Yes. Forget about the superscript. Look at the subscript. Yes. So that's why here is 100. You cannot put 0 here. No, cannot. Because this is T subscript 0. This one meaning here. You go here, you see, this is the meaning. This is the meaning. But here they don't write superscript, subscript because this is problem. So this superscript, subscript we created in the system and then we do it accordingly. That's why this is 100. Now this whole thing goes right hand side because we want unknown to be left hand side. What is unknown? Unknown is T1, T2. A superscript must be the same because you start with the level 0. When level L is 0, this will become 1, superscript 1. That means you already went to the x 2 cm, not x at 0 cm. So for I1, you created this equation. You keep this. You keep this. And then you move on to I2. I2 meaning at x 4 cm. The equation is the same, general equation. But the values are different. This one minus lambda. Minus 0.020875 T11 plus, because I is 2 now, so T subscript 1, 1 plus 2 lambda. Your I is 2, so T12 minus lambda. T31 equals to I is 2, T20. This one is minus lambda T31, T12, T11. So minus 0.020875 T11 plus 1 plus 2 multiplied by 0.020875 T12 minus lambda 0.020875 T13 equals 0. So we have unknown T1, T2, T3. The right hand side, this is 0 because this is T02 is 0. From where? From this one. Yeah, this one is 0. So you use all the value inside here. Now, I2, we already finished. I3 at x 6 cm. This is a general equation. You substitute I. L fixed already. L doesn't change, 0. So I3, 3 minus 1, 2. Here I3 minus lambda, 3 plus 1, 4. So superscript 1, 1, 1. Here L0, this is T3. T3 is 0. This is initial condition. So this is already given. Now you have T2, T3, T4. Now I equals to 4. Using same equation, but I is 4. L is 0. So 4 minus 1, 3. I4. This one 4 minus 4 plus 1, 5. This one 4. So T04 is 0. But T15, this is the temperature, initial temperature at X5 is 50. You have to be careful, class. Don't simply put all 0. No. This one different from this one. This one different. This one is 0. But this one is different. This is temperature at x equals to 5. Superscript, this is at level L0 actually. So when L0, this one become 1. But the level still 0. That's why it is 50. Now you simplify, you get this equation. Make sure you write it down at the moment. Later when you see the slide, you can go into detail. At the moment, just you can capture using your iPhone or any way. You just scribble, take down quick notes, yeah? Because I go slowly so that you can copy. Minus 0.020875 T3 plus 1.04175 T4 minus 1.04375. This one you cannot write left hand side, you must bring right hand side. The reason is we are creating the system called linear linear algebraic system, AX AT equals to B. So you collect all, you put like this. This one they're explaining how the equation created. 4 equation, 4 unknown, T1, T2, T3, T4, that's all. But you have a 4 equation. You create this equation from the finance different method. So what is the finance different method? What is the purpose of finance different method? In solving heat conduction equation, what is the role of finance different method? Is to create the system of linear equation. So the equation, general equation is already given. You cannot change the equation. The general equation, from this equation, you created the 4 equations. So these 4 equations, because this one, we very hard to see in the pictorial form. That's why you form the matrix like this. This is the nice way. But when you want to solve, you go back to the system. This one meaning 4 by 4 matrix, 4 rows, 4 column. This is called column matrix. T1, T2, T3, T4. The L is 0. L when 0, all superscript become 1. So this is what we call the next level, T superscript 1. But the temperature at X1, X2, X3, X4. You remember like that. This one is the nice way of writing. Right hand side, you get it from here. 2.085, 1.04375. This numerical computation is very important class. This is the hardcore of this study. You cannot solve analytically, not like Laplace transform. No, cannot. So this matrix is very unique matrix. But this one, 0. 0, T3, 0, T4. This one is tri-diagonal matrix. That means the upper part all 0 here. This one and this one 0. And the lower part here also 0. 0 T1, and then this one 0 T1, 0 T2. This one T3, T4. So you construct this matrix. It look very nice from the system because this one doesn't look nice. So when you have this system, then we know this is called simultaneous algebraic linear equation. Linear means not like x power 2, x power 3, the x power 1. So linear equation. Now we want to solve this using Gauss-Seidel method. That is the idea. So Gauss-Seidel method, you learn from this example, not for a theoretical point of view. From the example, you learn how the iteration works. So you repeat that when next time you solve the problem. So now we're going to explain to you how Gauss-Seidel method is used to solve this problem. So again, come back to this. You may ask why you write in the matrix form. After that, come back. Matrix form give you the picture. This is nice to see. But again, you just need these 4 equations. 1, these 2, these 3, These four. You need these four equation to solve. So Gauss-Seidel method, now we want to start. So in order to start Gauss-Seidel, the theory of Gauss-Seidel, we no need to go into detail, says you must start with initial guess. This one nothing to do with the implicit finance difference method. You already out now. There are two phases class. The phase one is about the implicit methodology. The implicit methodology for this case, you don't use any other method. To solve the system, you use Gauss-Seidel. But Gauss-Seidel has own way. What is the way? So Gauss-Seidel, you must start with the initial guess. This is new now. Who will give you this? No one will give you. You have to do on your own. So the theory says the T1 superscript 1, T2 superscript 1, T3 superscript 1, and T4 superscript 1 is 0 because this is the starting. We are now going to use a numerical methodology. We want to use the numerical methodology to solve. We call this as iteration 1. Iteration 1, the step 1 is to calculate the T11. It's a new value. You can see the value is different from this one. From 0, you already moved to 2.00384. So how do we get? This one is the title now. Equation 1, from here, from this one, you already have this. So from here, you want to calculate T11. So how do we calculate? We go to the steps. So T11 equals to 2.0875 plus. This fellow is minus. So bring right hand side, it become plus. Add 0.020875 T12. But T12 is 0. So this is very important. If you don't have this value, you cannot start. You don't put T12 on the left-hand side, cannot. You must find T11. This is the nature of Gauss-Seidel method. You must calculate T11. So according to this order, this is the order. So now you press your calculator, 2.0875 plus 0 divided by 1.04175. Can you get this answer? 2.00384. This is called numerical experiment. You cannot just follow like that. You have to use your calculator and confirm with me. Anyone can confirm, please? Yeah, Chia. Can you confirm, Chia? Yes, waiting, Chia. Yeah. Chia, can you confirm? Kelvin, can you confirm the value? Yeah. Okay, good. Okay. Good. Oh, all right. That means you are active now. You are active now. So you are aware. Otherwise, you cannot take it for granted because next time you want to use this. So the best thing is you better practice. If you don't practice, next time you will substitute wrong values. Then the next iteration will go wrong. So the best way is you practice now. Practice means it's just like a numerical experiment, laboratory kind of activity. You're not solving like Laplace. No, we don't use calculator very much when you use Laplace. That one is a really very tough analytical method. But here, 100% you have to use calculator. The question is 1 decimal, 2 decimal, 3, 4, 5, 6, 7, 8, and so on. To be nice, you just take 5, enough, 5 or 6. So 2.00384. If any discrepancies in the output, please let me know. So T11 already done. Now from equation 2, you go to 2 now. First one over already. From 2, you want to find T2. So how do we do that? You go here. This is T2. But the T11 no longer 0. You must use the new one. This is different class. Take note, yeah. So you have to use new value. You cannot use the previous value. No. So this is different. This is different. That's why you have to pay attention. This one is Gauss-Seidel. Many students will have problem later on. The T11 is updated value, meaning this one, yeah. But the rest still 0. This one still 0. Because you are finding T12 from the second equation. This is from second equation. You want to find T21. So 0.020875 T11, this one goes to right, plus this one negative, plus 0.020875 T13 divided by 1.04175. But the T11 is not 0. This is value 2.00384. You must be very careful here. Otherwise, your answer will be different. But T13 is still 0. This way, this iteration. So now you take your calculator, calculate 0.020875 multiplied by 2.00384 plus this is 0 divided by 1.04175, you get this value. This is T2, superscript 1, that's okay. 0.04015. This is from the second equation. Now go to third equation. Now we are in the third equation. This one to find T13, T3. So T12 already found. Now T13. So T13 is here. So you bring left hand side. Right hand side 0 plus 0.020875 T12 plus 0.020875 T14. But the T12 must take this value, new value, 0.04015. But T4 is still 0. This one, because you can see T41 is 0. Now you press your calculator, 0.020875 plus multiplied by 0.04015 divided by 1.04175. Can you verify this, class? 0.00081. Yeah, anyone can verify this? Yes. Anyone? Yes, Chia. Can you verify the answer? T3, 0.00081. Yeah, can you verify, class? Yes, Chia. You got to calculate, yeah. Can you verify? Validate? Yeah, Mohammed Dennis. What is your value? Can you type the value, please? Yeah, Mohammed Dennis. 0.00804. Okay, 8045. You can make it 804. 804. 804. Okay, there is 6 decimal places, but they want to make it 5 decimal places. 0.0081. Yeah. Okay. All right. Thank you. Muhammad Shalihin, yeah? Okay. All right. So we agree. This is 5 decimal place. Now we move on to T4. So T4, you have the fourth equation. This one very important. So T4 is here. So T4 equals to 1.04375 from the fourth equation, yeah? Plus this one minus 0.020875 T13. So 1.04375 plus 0.020875. The T13 must take this value, 0.00081. So you substitute that value here. Now you calculate the T14, 1.00194. Can you calculate that? This is iteration 1. We are going to complete. This is the last temperature, T4. T5, no need. So can you verify this, 1.00194? Do you agree with the value, T4? Yes. Shakir? T4, 1.00194. Can you verify this? Are you there, Kelvin? Kelvin? Chia, are you there, Chia? Yes, sir. Patricia, 1.001936, yeah. So we take it 194. All right. Thank you, Patricia. Yeah. So now, yeah, anyone else? Can you confirm? Mohammed Dennis, can you confirm the value? Yeah. Mohammed Dennis. Same, sir. Okay. Okay. All right. Okay, thank you. Mohammed Shalihin, Mohammed Dennis. Okay, good. Thank you. Good. So thanks for. Okay, thanks. All right. Good. So now you are in action, yeah? So you are really doing the practical work. So that is very important because you are going to do this next time. Now you have to do like this. This is nice way of putting. So now no longer 0, 0, 0, 0. This is solution after first iteration. So the heat conduction equation, we construct or we develop the what we call system of algebraic linear equation, and we solve the system or algebraic linear equation using the Gauss-Seidel method. Gauss is the name of the person, and the Seidel is the name of the person, the two people who invented the method. So now you can see, you put this nicely. T1, T2, T3, T4 is the temperature, 2.00384 temperature. Superscript, you don't worry very much because that is level. So what is important here is the first iteration. This is the keyword class, the first iteration. You see, when you do Rangikuta, Yoon's method, or Euler method in chapter 4, we don't use this word iteration because at that time it is not so important or so significant or so famous, because that is the beginning of numerical method, solving the ODE, first order. But now this is advanced. This is the hardcore of numerical method. We must use the word iteration. First iteration, you already got this answer. Now, The next one is we are solving this problem at t 0.1, but that is not the final answer. So this is different. The answer t at 0.1, but we use a numerical method already solved first iteration. But the first iteration is not final. We have to solve for second iteration. This is new class. Now the first iteration output is this one. Now we use the same matrix, but iteration different. But you calculate T11, still same. But the value will not be the same. Why? Because this is a numerical calculation. You see the answer is different. The temperature T11 is 2.00464. Is different from 2.00384. Even it is very slight different, but it is still different. So this is different. Until okay, so come back to this thing. Yeah, line cut off. Yeah, now okay. Is it okay now? Okay, slide. Can you see the slide? What about slide? Okay, I will upload again. Okay, just hold on. We're having internet problem class. This is a major problem class. Internet problem is a major problem. Can you see the slide now? Can you see the slide now? Suniljit? Okay, all right. So continue. This equation is to find the error. So we need to do at least minimum 2 iterations. The K here, the superscript K here is represent iteration. But in the problem, we use L. So we remove the L later on. I will show you how to switch to the K. And the I is the iteration 2, iteration 1. This K, the subscript I is the temperature, T1, T2, T3, T4. So you have to do 4 times. So K plus 1 and K are the present and previous iteration. These are the iteration. So this equation we will use later on. So you have to wait for iteration 2. First iteration, you already found this answer. This is iteration 1. Now iteration 2, you use this one. T1 2.00384, T2 0.04015, T3 0.0081, T4 1.00194. So you use this to calculate T11 for iteration 2. So T11, the same equation. You already constructed the equation. That equation, for equation, you cannot change. So 1.04175 T11 minus 0.020875 T12 equals to 2.0875. So you rewrite this again. T11 2.0875 plus 0.020875 T1 subscript 2 divided by 1.04175. Now the T12 you have to substitute 0.04015. Comes from where? Here, this one. So you calculate now, you verify, the answer must be 2.00464. Do you agree with this answer? Yeah, could you please verify this? Could you verify this, class, please? Yeah, anyone can verify? Yeah, could you please verify? Okay, good. All right. So iteration 1, iteration 2. For the T12, you use the second equation, this equation. But we are in iteration 2, yeah? Follow. Iteration 2, but you want to find T12. So T12 is here. So 0 plus 0.020875 T11 plus 0.020875 T13. So T11 is 2. The updated one, not the previous one. T11 is the updated one, 2.00464, and T13 is the previous one, this one, 0.0081. So you simplify, you should be able to get 0.04019. Please, you have to confirm this, class, otherwise we cannot move. Yeah, we need to verify numerically, sort of experiment. So could you please verify? 0.04019. Yeah. Anyone else? Chia, are you there, Chia? Yes, please, Chia. Yeah, go ahead, Chia. We are waiting for you, Chia. Chia Cheng. Could you verify 0.04019? Anyone can verify the value for T2? Muhammad Dennis, 0.040, check please, 0.04019. Yeah, Muhammad Shalihin, 0.04019. Good. Okay, great. Okay, so now, okay, good. All right, now we move on to T3 from the system. The third equation, this one. Don't change this equation. This one you already done. So what you have to do, you have to find T13. So you bring left hand side, T13, the rest goes to right hand side. 0, this fella, this fellow is 0 plus 0.020875 T12 plus 0.020875 T14. T2, the value is 0.04019. This is the updated one, the new current one. T4 is the previous one. This one from iteration 1. So 1.00194. So you calculate all this, 0.020875 multiplied by 0.04019 plus 0.020875 plus multiplied by 1.00194 divided by 1.04175. You should be able to get 0.02088. This is how you have to practice, class. You cannot take it for granted, because if you just follow the notes without calculating, doing, very difficult for you. Next time, if you ask to solve, you may plug in the wrong values. So make sure you plug in the correct values and then get the correct output. So T3, 0.02088. Can you confirm this, class? Could you please confirm T3? 0.02088. T3. Yes, Gabriel. Gabriel, yeah, we are waiting for you. Please verify the answer. 0.02088. 0. Mohammed Shalihin, Gabriel, 0.2088 yet. Yeah, yeah. Okay, great. All right. So you already have T3, not yet finished. We have to move on to T4. So T4 from the equation number 4. This equation don't change. This is the fourth row. So T4 is here. You don't worry. T4 is here. So T4 superscript 1 equals to 1.04375 plus 0.0. That's why this fellow is keep on reducing. No more already. So we are in the last temperature T4. So T3 0.02088. Now you calculate 1.04375 plus 0.0208875 multiplied by 0.02088 divided by 1.04175. You get this answer. 1.00234. So you have to verify this, class. T4, 1.00234. This is the last temperature. So it's different from this one. Yeah, this one is the iteration 1. This one is iteration 2. But the symbol same. That is different. This is new. This is iteration. Iteration 1, iteration 2, iteration 3, iteration 4, and so on. So could you please verify this 1.00234? Anyone? Yeah. Yeah. 1.00234. Yeah. Okay. All right. Okay. All right. Thanks. Now, yeah, 2338, we can make it 234. Yes. Yeah, nor ein. Can make it 6 decimal. Okay. No need to go more than 5 decimal. 1.00234. Even you use 2338 is okay. All right. Now the thing is, you already have this T2. So now you have solution after second iteration. If you compare with the first iteration, this is different. Why it is different? Because you are using the Gauss-Seidel method. You are updating the temperatures. So this is the correct way to put the final answer. So you have first iteration. The answer T1 is 2.00384. T2 0.04015. T3 0.0084. T4 1.00194. Forget about the superscript. The superscript just we are in the level 0. So it became 1 now. So the next level. So this temperature is second iteration. Now, the first iteration, the temperature is like this. Iteration 1 is this one. This is what I read just now. So, iteration 1, you have these 4 values. Iteration 2, you have these values. Now, we want to calculate, this is new, slide not available. You go back to this one. We are going to do this one. Slide number 23. This one epsilon. Epsilon s is not given, so we don't know epsilon s. We can calculate the epsilon. The modulus of epsilon is Ti superscript k plus 1. What is the meaning? I is the temperature. You can start with I1 because we already started with I1. So you write down T1 superscript 2 minus T1 superscript 1 divided by T1 superscript 2. That means K plus 1 is the next iteration. K is the previous. So second iteration minus the first iteration for T1 only. So your answer will be, write down, yeah, T1 superscript 2, 2.00464 minus 2.00384 divided by 2.00464 multiplied by 100%. Can you calculate the answer? The epsilon, we are calculating the epsilon. It must be positive value, yeah? If it's negative, you make it positive. So what is the percentage? You can give me a 2 decimal number, okay? Because this is percentage. Of course, it's more than 2, it's okay. But 2 is better, 2 decimal. We are calculating the percentage. So this is one of the important study so that we can move to the next method with the reason why we want to study another method. So can you calculate the epsilon class? What is the answer? .00464. Temperature 1 only, yeah? We are calculating at temperature 1. Mohammed Dennis, yeah? 2.00461. You already got temperature 1. Iteration 2. 2.00464 minus 2.00384 divided by 2.00464 for temperature 1 only, yeah? T subscript 1. Multiply by 100%. So what is the answer? 0.04. Wonderful, Natasha. Yeah, great. I got 0.03, 0.04%. Yes. Yeah. 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 Nice. Yes. So that means it's very accurate. Very good. 0.04% is less than 1%. That means 99% accurate. Only for temperature 1, yeah? Now we want to calculate for temperature 2. Not finished yet. Temperature 2. That is T1. Now the temperature 2 is T2. T2. So T2, the T2, the K plus 1. So you have temperature 2 is Ti, still Ti, but T2, T subscript 2. So the K is already fixed. K is fixed. The I is different. I is T2. Of course, power is 2. K plus 1. K is 1. So T2 power 2 minus T2 1 divided by T2 2. So I is 2. Now I is 2. You calculate 0.04019 minus 0.04015 divided by 0.04019 multiplied by 100%. This is for T2. T2. Epsilon for T2. So I repeat again, yeah. So using this formula, you calculate 0.04019 minus 0.04015 divided by 0.04019 multiplied by 100%. 1 decimal place. 1 decimal place. Muhammad Shalihin. 1 decimal place. 0.10%. Yes. Yeah. Yes. Yeah. 0.1%. No, Muhammad Shalihin. Symbol is missing. 0.1%. Yeah. So 0.1% is good. But 0.04 is less than 0.1%. So T1 is better than T2. So the T1 is more stable, reliable. But T2 also good. But compared with T1, the error for T1 is very less. But we cannot say T2 is not good, because this if you take 100% minus 0.1, it's almost 99.9%. Correct. So you already obtain the error for temperature 2. Remember, yeah, if you ask to calculate error, this is the way how to calculate the error. You learn now how to calculate the error. How to calculate the error. How to calculate the error. This is the way. This is the correct way to calculate the error. This is the way. All right. Now we move on to epsilon 3. Epsilon 3 for temperature 3 is 0.02088 minus 0.0081 divided by 0.02088 multiplied by 100%. This is for T3. Yeah. Percentage, yeah? Put the percentage. How many percent? It can be more than 1% also. It can be 10%, 20%. But it must be in percentage. Error must be in percentage. 0.02088 minus 0.00081 divided by 0.02088 multiplied by 100%. So what is the value? 96.12. Yes. Yes, yeah, yes. Yeah. Okay, excellent. But the problem here is, this is the error. So you see the error is very high, 96.12%. So the error is very high. But we leave it that for a while, yeah? So you see, compare with temperature 1, temperature 2, temperature 3 is not very good, okay, in terms of the error, because the error is 96%. Now, yeah, class, can you see the slide, class? Hello, can you hear me? Class,
Yes, sir. Yes, but we cannot see the slide.
slide, no. Okay.
No slides.
Oh, all right, wait. Slide is, wait a minute, yeah, please. Internet problem, yeah. Okay, still we are here. Okay, now we move on to slide 23 still. Okay, you try T4. T4 now. Mohammed Amir, yeah. Class T4 now. T4, the error 1.00234 minus 1.00194 divided by 1.00234 multiplied by 100%. Calculate the error. T4. 1.00234 minus 1.00194 divided by 1.00234 multiplied by 100. Yes, correct. Yes, perfect. Anyone else? One verify 0.04. 0.04%. So anyone else? Muhammad Ali? Can you confirm this, class? Muhammad Ali?
Yes, sir. Yes, yes.
percentage sign is missing. Mohammed Dennis, 0.04% percentage. PERCANT percentage 0.04%. Yes. 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 Okay. Now you analyze. Now analysis. Now we analyze. The T1 is 0.04%. So T1 and T4, the error are the same. T1 error is 0.04%. Good. T2, 0.1%. It's okay. But T3, 96.12. This is not okay. Too high. But T4, 0.04%. This is good. So therefore, class, for this problem, we couldn't obtain T3. So T3, the error is too high. T3, for T3, the error too high. So therefore, we have to look into another methodology. This is how the mathematician or the scientist, the great inventor, they develop the new method to answer why we need another method. This is what we call philosophical question, class. Of course, you can study for further studies, masters and PhD, to study this problem now. We are having a major problem. We cannot say this method is very good. That means here we have two things. Phase one, the implicit method, simple implicit method. We can say this method is average, not so good. Because Gauss-Seidel, you cannot say it is good or bad because it just solves the system. So we cannot find fault or condemn or say something very bad about Gauss-Seidel, because Gauss-Seidel is just to solve the system. But again, Gauss-Seidel also have problem because of the initial guess. So it's very hard to pinpoint what are the factors that contribute to this error, which is too high. But we can predict, and then we can say from the output, the method which is called as simple implicit is just an average method. So what is the solution, class? Solution is we have to move on to another method. So another method is called slide number 43. So slide number 43 is called Crank-Nicholson method. So altogether, three methods under FD methods to solve heat conduction equation. Three methods: explicit, implicit, one is Crank-Nicholson method. But Crank-Nicholson method is almost similar to method. You create the system. After that, still we are using what we call Gauss-Seidel. But the Crank-Nicholson creating the system of linear equation is different. More what we precise, more accurate. that can be judged by the error. That we can do later in the next lecture, finding the error for Crank-Nicholson method. For today, I just want to show you the development of the system of linear equation. So Gauss-Seidel, you already understood. Anyone got problem in Gauss-Seidel class? Anyone cannot understand Gauss-Seidel? Anyone? Anyone? You have understanding problem on Gauss-Seidel? Not clear? Hello? Is it okay so far? Yeah, Muhammad Ali. Muhammad Ali, is it okay?
Yes, it's okay.
All right. So the reason why we want to study Crank-Nicholson method is we hope we can minimize the error to teacher 4. But it doesn't guarantee, because it's very hard to say whether the final output will be accurate to very high percentage accuracy in terms of the error. So now we want to do two things. One is Crank-Nicholson method to develop the system, and then we solve the system using the same Gauss-Seidel method. So we don't study new method, no. So we will still use Gauss-Seidel method. Now what is Crank-Nicholson method? For Crank-Nicholson method, the spatial derivative, the del squared t del x squared, is approximated by an average of two central difference quotients. A central difference quotient, one evaluated at L, the other one is L plus 1. L plus 1, the level. So you can see the centered finite difference, they are taking average. TL plus TL plus 1 divided by 2. That is the meaning. But this term all will be given to you. You no need to memorize. This already well developed in the numerical method. So we will use this, plug inside the partial differential equation, del squared t del x squared, and forward finite difference for time domain, del t over del t minus TL plus 1 minus TLI divided by del t. So this average, the average they are talking about is for the distance, but this formula is still the same. Now we substitute back inside the famous heat conduction equation. Left hand side, right hand side. So what they do here, the T superscript L plus 1, all you collect left hand side with lambda K del T over del x squared. Of course, these two you can bring in left hand side. It becomes 2 TL plus 1. So this one is 2 TL plus 1. And then minus T L I, it goes here. This one. These two TLIs here. So the TL superscript L all right hand side. This is how you recognize. This equation will be given for information. You no need to memorize. This equation will be given. It's very hard to memorize. It has 1, 2, 3, 4 left hand side and 4 terms right hand side. So terms altogether.
Excuse me, sir.
Yeah, yes, please.
The slide is not moving.
Is it? Now slide number 44. Not moving?
We are now on slide 23.
Okay, so I upload again. Oh, suddenly it's not moving. Okay, now I upload again. Okay, slide 44. Can you see slide 44?
Yeah, now can, sir. Thank you.
All right. So slide 44 comes from slide 43. Can you see 43 now? 43.
Yes, can, sir.
43, yeah? So 43 is just introduction. And then 44 is the equation. Now we want to use this equation. Minus lambda t superscript L plus 1 subscript I minus 1 plus 2 multiplied by 1 plus lambda t superscript L plus 1 subscript I minus lambda t superscript L plus 1 subscript I plus 1 equals to lambda t superscript L subscript I minus 1 plus 2 1 minus lambda t superscript L subscript I plus lambda t superscript L I plus 1 subscript. So lambda is k del t del x squared. Now this is the computational molecule for the Crank-Nicolson method. The grid point involved in time difference x-axis TL and then TL plus 1, in between TL plus half. Half is because 1 divided by 2. So that is the average they are taking. Just now you saw divided by 2. And then the vertical axis xi minus 1, xi plus 1. So slide 46. Can you see slide 46, class? Now 46. Now we are in slide 46. Gabriel, can you see Gabriel? Slide 46. Gabriel? 46. Okay. All right. So slide 46. Example, still they're using the same name, example 1. But we already solved example 1 2 times. This is third time. Third time, still you want to find the temperature at T 0.1 second. And today I will not take long time. We will not go into solution yet because the answer is given, but we can do in the next lecture. But I explained to you how to create the system. The Crank-Nicolson method, the equation is different. This equation is different from previous implicit and explicit method. That's why we call it Crank-Nicolson method. So for this problem, you must use Crank-Nicolson method. So if you ask to solve using 2 or 3 methods, then you have 3 options. So altogether 3 methods only within the syllabus. We don't have method 4. No. Any other method, you keep it for future studies. If you search various methods to solve heat conduction equation by using numerical approach, you will find many methods. So we stick to 3 methods: explicit, implicit, Crank-Nicolson. So use the Crank-Nicolson method to solve for the temperature, capital T, for a long thin rod with length 10 cm. So 10 cm meaning the del X is 2 cm. This is step size, class. Step size 2 cm. So what is the meaning? Meaning is 0, 2, 4, 6, 8, 10. Very simple. So the del X is 2 cm. But the del T 0.1, because you are going to calculate the lambda, they need the del T. At the T0, the temperature of the rod is 0. This is capital T, 0, when the time 0. This is what we call initial condition. But the boundary condition are fixed at all times. Fixed at all time means the capital temperature at x is 0. That 0 is this is x. At the distance 0, at any time, temperature is 100 degrees Celsius. This is the initial temperature at x0. At x 10 cm, this one meaning 10 cm. I'm using the snapshot. Yeah, temperature is 50 degrees Celsius. The unit all you must be very familiar, class. Units are very important here. Otherwise, we do not know which one is which. The meaning will be represented by the units. The symbol, the notation must be explained by the units. For example, this is T0 second. They miss the word second, S. The small letter S stand for second. The cm stand for centimeter length, because we have to identify the representation of the parameters. The parameters represent what? Temperature, distance, time, volume, area, what is that? So the K value you don't create, it's already given. So we want to find the temperature at T0.1. So from T0, the next one is T0.1. After that, T0.2, 0.3, and so on. So we have very much highly limited studies, yeah? So we limit ourselves. Now we want to create the system. So we will stop after we create the system. It looks same, discretize using Krein-Nicolson method, meaning we want to find the system of linear equation. System of linear equation. First, you have to calculate the lambda. You see, you must practice this. Otherwise, you will face difficulties in the future. So lambda equals to k del t divided by del x squared. So what is your k? 0.835. What is del t? 0.1. What is del x? 2. So 0.835 multiply 0.1 divided by 2 squared. 4, you should be able to get 0.020875. Okay, make sure you get this value. Now, the initial condition and the boundary condition are given like this. You must take note here. The T00 is the temperature at x0. This one. And then temperature x equals to 10 is T subscript 5 equals to 50. T0 subscript 5 is 50. The rest is 0. That is the meaning, initial condition. The capital T at time 0 is 0. So at any other time, meaning the subscript 0 and the subscript 5 is 150. So using this value class, you create the system. As I said, the system like this. The T superscript L plus 1 left hand side, T superscript L all right hand side. You rearrange this equation in this form. This is called standard form. So at I equals to 1, you form the linear equation. So minus lambda Ti1 T naught superscript 1 I L0 fix L0 plus 2 multiply 1 plus lambda T superscript 0 plus 1 1 subscript 1 I is 1 minus lambda T superscript 1 subscript 2 equals to lambda T superscript 0 subscript 0 plus 2 1 minus 1 minus lambda T superscript 0 subscript 1 plus lambda T superscript 0 subscript 2. These values, all these values you can find, including the minus lambda T21. Sorry, minus lambda T naught naught. This is 100. This one is 100. T10, 2, 1 minus lambda. T10 is 0. And then lambda lambda T naught 2 is 0, and then lambda T naught 1. This one is not 0. This is 100 class. Why? Because at x0, this is 100. Take note, yeah? Superscript is 1 because at L0, this happened to be lambda 0 plus 1, 1. So this one is x0. That's why this is 100. Now you form the left hand side is the unknown T1 and T2. The rest all goes to right hand side because we are creating the system, the linear system. So all the constant is right hand side. If you notice this one T naught naught, yeah, T naught naught still 100. Make sure because this is T subscript 0. At same time, the T naught 1, this also 100. No different because this is at x still 0. Only the superscript 0 and 1, but that doesn't affect the temperature at x0. The main point is at x0, this subscript. That's why this is 100, this is 100, rest is 0. So you multiply and then add, you should get 4.175. So if you simplify, you get 2.04175 T11 minus 0.020875 T12 equals to 4.175. Can you get this equation, class? Can you create this equation? Yes or no? Can you? Yeah, Ahmad Azhari. Yeah. Any question, class? Can you get the first equation? Yes or no, class? First equation. Natasha, okay. All right, so you already have the first equation at I1, x2 cm. At I2, x4 cm. So the subscript will change because I2, this is T subscript 1, this is T subscript 2, T subscript 3 equals to T subscript 1, T subscript 2, lambda T subscript 3 because I is 2. Now this value T11, this is T21, this one T31. So this is T11, T12, T13, all left hand side. Right hand side, lambda T0 0 plus 2, 1 minus lambda, T0 2 also 0, T0 3 also 0. So the right hand side all 0. The unknowns are T1, T2, T3. So you get this equation. So this is at I equals to 2. Can you get this equation, class? Unknown T1, T2, T3. The rest all move to right hand side. This is at I2, x equals to 4 cm, L still 0. Okay, class? Can you get the second equation? Chow Jit, yeah. Who is Ahmad Azhari? Are you there, Ahmad Azhari? Ahmad Azhari, are you there? Okay, good. Okay, so Jaujit already got. All right. Now I3, very important, yeah. I3, L still 0. So you have lambda minus lambda T2 plus 2, 1 plus lambda I3, T3 minus lambda 3 plus 1, 4 equals to lambda 3 minus 1, 2 plus 2, 1 minus lambda I is 3, T3. And then I plus 1, T4. So T21, T31, T41 all left hand side. And the right hand side is minus lambda T02, 0 plus 2, 1 minus lambda T30, 0 again, T40, 0 again. Therefore, right hand side is 0. So you have this equation. Minus 0.020875 T2 plus 2.04175 T3 minus 0.020875 T4 equals to 0. Can you get this equation, class? Could you please verify this? Can you verify, please? Third equation. Yeah, anyone? Gabriel? Could you please verify, Gabriel? Third equation. Mohammed Iskandar. Yes, sir. Okay. Anyone else? Correct, sir. Okay. Good. Now, okay, thanks, Gabriel. Now we move on to I4, the last one, at x8 cm. I5, no, is already given. But here you must be careful. I4, this is minus lambda T3. This is T4 minus lambda 4 plus 1, 5. T5 equals to T4 minus 1, 3 plus 2, 1 minus lambda I4 plus lambda I plus 1, 5. So you have this equation and you substitute all the value. Minus lambda T13 plus 2, 1 plus lambda T14 equals to lambda T03, 0, 2, 1 minus lambda T04 still 0. T05, this is not 0. This is 50. And then the lambda T15 is from here. This one goes right hand side is 50. This one you have to be careful because this is at x5. This one also at x5. So the temperature at x5, this is T5, is 50. This is 50. And now you calculate, you should be able to get this. Minus 0.020875 T3 plus this one, the 1 plus 0.020875, you can simplify. You get 2.04175 T4 equals to this whole thing. You simplify, you get 2.0875. So this is the fourth equation. So can you get this equation? Can you verify this, class? I4, the fourth equation. Yeah. Muhammad Aikal. Okay. Okay, good. Okay, we already come to the end. So now we have I4, I3, I2, I1. So we will have this system. This system is different. Different meaning here different values. But the system is 4 by 4 matrix. 4 unknown, T1, T2, T3, T4. 4 unknown and 4 equations. So you can find unique solution. So 2.04175 T1 minus 0.020875 T2 equals to 4.175, equation 1. Equation 2 minus 0.020875 T1 plus 2.04175 T2 minus 0.020875 T3 equals to 0. For I3, minus 0.020875 T2 plus 2.04175 T3 minus 0.020875 T4 equals to 0. This is third equation. Fourth equation, I equals to 4 minus 0.020875 T3 plus 2.04175 T4 equals to 2.0875 at x equals to 8 cm. We don't have I5 because at I5, T5 is given. We don't have I0 because T0 is given 100 degrees Celsius. Now we have this system. This is called the matrix, tri-diagonal matrix, because on the top here all 0. The first row T3 T4 and this one is T4 0. So it looks like trigonal matrix. On the bottom here this is 0 and these two elements here are zeros. So therefore this system is called tri-diagonal matrix. So in order to solve this, we create the system again. So we will do next lecture how to get the solution. This is for first iteration. To solve the system, this one, still we use Gauss-Seidel method. If you have time, you can solve, and next lecture we can verify this answer, whether correct or not. So next lecture will be on this. First iteration 2.04481. Second iteration temperature T2 0.02091, and then temperature 3 0.00021, temperature 4 1.02241. This is first iteration. So if we can do 2 iteration, we can do in the next lecture, then we can find the error, the convergence epsilon. So that's all for today class. So if you have any question, you can ask me now before we stop. Yeah, any question, class? Any question, class? Yeah, any questions before we stop? So if no question, shall we stop here? Shall we stop here, class? Shall we stop here? Hello? Shall we stop here?
Yes, sir.
Okay, thank you very much. See you again. Thanks a lot.
Thank you, sir. Goodbye.
Welcome, welcome. Yeah, goodbye. Bye. Thanks a
Thanks,
lot.
sir.
Have a good day. Have a good day. See you again. Please
You
fill up.
too, sir. Bye.
Yes, please fill up your satisfaction poll. Please fill up your fill up. Please fill up your satisfaction poll, class. So we need this, and then your SSRT via U campus. So a lot of work to do, and then cost outcome survey. Please fill up, yeah. SSRT via U campus. Sorry, U campus. Sorry, U campus. Sorry, U campus, yeah. And cost outcome survey. You are cost outcome survey. So a lot of things. So see you in the next lecture. All right. So I will stop here. Hang up, yeah.